Here I've drawn two blocks of silicon material. Let me complete the block on the right. The circle represents the nucleus of the silicon atom. And each silicon atom has 4 electrons in the outer shell. And I'll represent these electrons as these dashed lines. So between these two nucleus, I have 2 electrons and 2 electrons to the next over on the other side. Now, suppose I want to add some impurities to the block on the left, and I want to produce what's called an N-type silicon. And on the right, I want to introduce a different impurity and cause a P-type silicon. So to do this, I could replace some of these silicon atoms with phosphorus atoms. So let's take this silicon atom over here, and we'll replace it with a phosphorus. And a phosphorus atom, instead of having 4 electrons in the outer shell like silicon, it has an extra electron. It has 5 electrons. So I have an extra electron associated with this phosphorus atom. If I replace this silicon atom with a phosphorus atom, I end up with an extra electron I'll draw over here. Now, if I were to apply an electric field or apply a positive charge on this side and a negative charge over here, I'll set up an electric field in this silicon bar that is in this direction. And what will happen is the electrons will be attracted to the positive plate. So the electrons are fairly free to move about. And so this insulating material, because I've added phosphorus to it, it now becomes a conductor. I have a source of charge that can move, and moving charge produces current. So let's take this block on the right side, and I want to convert this from this intrinsic silicon to a P-type material. And I'm going to introduce some boron atoms. So I'm going to replace this silicon atom with a boron atom. And now a boron atom, instead of having 4 electrons in the outer shell like the silicon, it has 1 less electron. So let me come over here and let's delete this electron right here. And let's replace this silicon atom with another boron. And let's erase this electron, since the boron atom only has 3 electrons in the outer shell. So look what can happen now. If I apply a voltage by putting a positive charge on this side and a negative charge over on this side of the block, again I set up an electric field in this direction. So we'll call this E field, and this is a direction of the force on a positive charge. Now these boron regions can be thought of as a positive charge. And look at what can happen. If I put a positive charge on the right side, this electron could be attracted to that positive charge and move over here. So let me erase this electron since it has moved. Now notice that, let me change color here. This silicon atom is missing an electron, so it can be thought of as a hole or a positive charge. Now look what can happen. This electron can now move over to fill this slot. So let's remove this electron here and add it over here. So now my hole has jumped over to the left 1 notch. The same thing can happen to this boron atom drawn at the bottom. So what happens is I get a net flow in this direction of positive charge, or we call it hole. The holes are positive charge that will move to the left. And in the end silicon, the electrons are negative charge that move to the right. There's a property of silicon that's called mobility, and that's denoted by the Greek letter mu. And the mobility is equal to the average drift velocity of the carriers divided by the strength of the electric field that I'll call E. Now this drift velocity, or V sub d, is a measure of how the electrons in the n-type silicon, how they are free to move to the right towards this positive charge. The drift velocity in the p-type silicon is a measure of how free the holes are to drift to the left towards a negative charge. Now, I'm going to ask you, what type of silicon would you think would have the highest drift velocity? Well, if I were to guess, looking at these electrons in the n-type silicon, they're free to move about. There's not much, they can move in any direction. They're kind of free objects, where the motion of the holes to the left and the electrons moving and filling these slots, that motion is more restricted. So I would think that the drift velocity would be better or higher in the n-type and lower in the p-type silicon. And indeed, this is the case. So if I have a very small electric field in the denominator, so this is very small, and I have a very high velocity of drift, then I have a very high mobility. So it turns out that my guess that the n-type mobility is better than the p-type mobility, that is a correct guess. And that has some consequences. So let's explore those consequences now. So what is the consequence of the mobility of the electrons in the n-type material being greater than the mobility of the holes in the p-type material? Let's explore that a little bit. Let's say I have a surface of a silicon wafer. And this is the wafer thickness. On this left side, I'm going to make an NMOS transistor. I'm going to put an N region in here, and I'm going to put another N region in here. I'm going to grow a very thin region of glass in the center between these N regions, and on top of that glass region, I'm going to put a gate electrode up here that is a conductive material. And if I apply a positive voltage to this gate relative to the N material, I create an electric field in this layer between the gate and the source drain area. So if we say this is a source, this is a drain, this is p-type material here. So if I set up an electric field in this region, this attracts negative charge to the surface. It creates a bar of N material here. And I have conduction between the source and drain. Now, if I do a similar thing over here, I put in a p-type material instead of an n-type. I put another P-type material, and I'll put in a region of N-type over here. This is N-type, and again this is P-type wafer. And I grow a thin oxide, a very thin glass region between these P regions, and on top of that insulating region I'll put an electrode, which is this material here. Now if I make this electrode negatively charged relative to the, call this the source and this the drain, I create an E field in this insulator region, and I attract P-type material to the surface here. So this causes conduction between the source and the drain. So since the mobility of the N-type material is greater than the mobility in the P-type material, this transistor at the left, which is a NMOS transistor, will have better characteristics than the transistor on the right, which is a PMOS transistor. So let me scroll down here a little bit. And the symbol again for the NMOS transistor is this, and the symbol for the PMOS transistor is similar, but a little bubble in the gate. So if this is a source drain, that corresponds to this source, this drain. If this is a source connection, drain connection, that corresponds to this source and this drain. This is my gate material. That corresponds to this, and the NMOS has a gate material here. That corresponds to this connection. So if you're designing an integrated circuit and you have your choice whether to use an NMOS or PMOS transistor, always go with the NMOS because it's based on an N-type material and it has a higher mobility and conducts better.